Okay, Assalamualaikum and hello. Welcome back to the fifth class of CCS 591. Okay, so let's continue with the topic of today. Yeah. So for today, we are going to continue the lecture for the topic of statistical estimations. Okay, but before that, let's recap back what we have go through last week on week 11. Okay, we already covered last week on the topic of statistical hypothesis testing that's include the procedure, the statistical test that include the Z test and also the p-value test, and also on one tail and two tail test, right? So I do hope that you have the ideas here on the hypothesis. What is a hypothesis, right? So actually, hypothesis is referring to one hunch or assumption to be proved or to be disapproved. Okay, by developing the null hypothesis and also the alternative hypothesis, right? So also I do introduce the term of level of significance, which refer to the risk the experimenter is willing to take of rejecting the null hypothesis when it is true, right? So the common set for the level of significance normally we set at 0.05, yeah? Also, we also introduce the p-value term is actually the probability of obtaining a test statistic to a more extreme, right? Then the actual sample value given the null hypothesis is true, right? So this is called observed level of significance. Okay, so the smallest value of null hypothesis that can be rejected. Okay, so if p-value is greater or equal than significant value, we do not reject the null hypothesis. Yeah. So if the p-value is less than or equal to significant value, then we reject the null hypothesis. Okay, there is some of the rules that we introduce if we use the p-value model. It has a decision, a tool that to whether we want to reject or accept the null hypothesis. Okay, so for today, we're going to cover a topic on statistical estimation. How we going to estimate the statistic, okay, by using the parameter estimation, point estimators, and also the confidence interval, right? Okay, so statistical methods are used to make decisions and draw conclusions about one population, right? So this aspect is called the statistical inference, right? Statistical inference is divided into two major areas. They are parameter estimation and also hypothesis testing that we covered last week, right? So for today lecture, we're going to focus only on the parameter estimation. So what is the parameter estimation? So parameter estimation use sample data to compute a reasonable guess of a population parameter, while the hypothesis testing used to make decision regarding a hypothesis about a population or sample, right? Okay. So in detail, parameter estimation is a statistical estimation is the process of making inference about one population based on information obtained from a sample from that population, right? So an estimate of a population parameter may be expressed here in two ways. The first is point estimate and the other one is interval estimate. Okay, so what is the point estimate? So a point estimate of a population parameter is a single value of a statistic. Okay, the sample mean, for example, the sample mean is a point estimate of the population mean, which normally stated in mu symbol, right? So for the interval estimate is defined by two numbers. between which a population parameter is said to lie. That is why we call the interval estimate. Okay, here is an example or an explanation of the population and also sample. Okay, so let's say we have this one population. We want to know about this population. We have the parameter statistic, which is population mean, which is mu, population standard deviation, which is sigma, and population proportion. And then we take a random selection from that population, and then we use, this is what we use as a sample. We take it based on the random selection, and then it will produce one sample. Statistically, it will produce a value such as sample mean, sample standard deviation, and also sample proportion. And then this value, the statistical value from the sample, will draw some inference of the population. Okay, from the statistical value of the sample, then we can infer what is the value of the population mean, population standard deviation, and also the population proportion. Okay, now, so the theory of estimation is part of statistics that extract parameters from observation. They are corrupted with noise. Sometimes the data is not clean, so it will be corrupted with the noise. Right? To determine the value of parameters through measure and observe empirical data. The process of estimation is carried out in order to measure and diagnose the true value of a function or a particular set of population. It is done on the basis of observation on the samples, which are a combined piece of the target population or function. Several statistics are used to perform the task of estimation. Okay, we need some statistical analysis, yeah, in order to do a estimation. So there are some properties here for an ideal estimator. So for an ideal estimator, the property should be unbiased, it should be efficient, and it should be consistent. Okay. Now let's look deeper, yeah, on every stated properties for the ideal estimator. Right? The first one is unbiased. Okay, the first property of ideal estimator is unbiased. What is unbiased? Okay, the mean or expected value obtained from sample is equal to the parameters being estimated. Okay, so the estimator, they are unbiased while performing estimation are those that have zero bias result for the entire value of the parameter. Right? So going by statistical language and terminology, unbiased estimator are those where the mathematical expectation or the mean proves to be the parameter of the target population. Right? So there will be no bias, right, on that estimator. Now for the second property is consistency. Okay? As sample size increases, the value of the estimator approaches the value of the parameter estimated. So this is what we call a consistency property in ideal estimator. Right? So if the estimator that give consistent estimate are said to be consistent estimators. As the number of the random variable increase, the degree of concentration will be higher and higher around the estimate in order to make the estimator of estimation the consistent estimator. Okay? So if the estimator gives an unbiased estimate and the variance of the estimator comes out to be zero, then the estimator of estimation is called the consistent estimator. Right? So it full that characteristic. Okay, so these two conditions need to be fulfilled only if the numbers of random variables reach infinity. Now, the third property of an ideal estimator is efficiency. Okay, of all the statistics used to estimate a population parameter, the most efficient estimator has the smallest variance. Right? So in estimation, there are many estimators that have ample incidences of consistent estimators. And according to the property of efficiency in estimation, the consistent estimators should be normally distributed. Remember, it should be normally distributed. This kind of property was taken into account in the theory of estimation because there were incidents of the estimators having ample consistent estimation but were not the efficient estimators. Okay? So here are the example of the point estimator. Point estimator. You want to measure a central tendency of the data. So the point of estimator will be mean, median, and also mode. If you want to measure of dispersion, so the point estimator will be the variance and also the standard deviation. So you want to measure the asymmetry of the data, then the point estimator will be the skewness and kurtosis. So this is how we measure the central tendency, the arithmetic of the mean, right? So yeah, mean is the simplest measure of central tendency, but is affected by the presence of outlier or extreme value. So as shown in the figure in the slide, you can see that the position of the mean, okay, the second line, if there is an outlier, how is the mean move? Okay, right? So the mean, yeah, the value of the mean, yeah, is easily affected by the presence of outlier or the extreme value. Okay. Now, second one is a measure of central tendency is the median. Okay. Median is a measure of central tendency with half of the value larger and half with the smaller. Okay. So let's say in the population or the sample, the n is odd, so the median would be the middle value, right? Else, how are we going to calculate the median? If it's, the population is not odd value, if it's not odd in total, so the median will be equal to mean of the two middle value, right? As shown in the formula in the slide. Okay. So if you can see, yeah, in the diagram, is the median affected by the outlier? Not really, right? It's not that obvious, right? It's not. It's not. It's not. It's not affected by the outlier. Only mean affected by the outlier. Now, the third one is the mode. Measure of central tendency is the mode. Mode is the most frequently occurring value in a sample series. Okay, the one that have the highest frequency, right? So mode is a positional average and is not affected by extreme values, just like median, right? However, mode may not exist or may not unique, right? So for example, in the bimodal distribution, there will be two values occur with the same frequency. So in that case, there will be no mode lah, right? So somehow, yeah, mode is the value, a central tendency value that often neglected in a statistical parameter. This has been discussed, yeah, in detail in the mode and neglected statistical parameter in the Journal of the Royal Statistical Society Series A, Desktop. Okay, you may read it in more detail in that journal. But why, yeah? Why is that the mode is often neglected in the statistical parameter? Okay. So yeah, I just summarize, yeah, what's in that paper, what's in the journal, right? So the mood has proved to be relevant in many situations involving efforts at rational decision making under uncertainty, right? For example, okay, we a shoe manufacturer, if for some reason forced to manufacture one size of shoes exclusively, it seemed reasonable that he should concentrate on the model size in order to maximize his sales. It is easy to conceive of analogous example in the realm of manufacturing and retailing. For example, choice of standard package. Okay. Another example is that in an election campaign, the party may be interested in picking the most popular issue to make them their respective issue. This is how, yeah, why the vote shouldn't be neglected. Okay. And then another example is that the mode is used to express the most likely outcome. Okay, the application involves a forecast, right? In meteorological forecasting or probability, this sensitive function may be used to specify the amount of rain in a future period. If the forecaster must pick one single figure and his reputation depends on his record of correct forecast, he should clearly pick the moon, the one with the highest frequency. So this is all the example that shows that we should not neglect the moon as a statistical parameters. Okay. So here is sampling distribution. Okay. Do recall that before data is collected, observation are considered to be random variable. Right? For example, x1, x2, x3, and dot dot dot. Right? So therefore, any function of the observation or statistic is also a random variable. For example, the sample mean and sample variance are statistic and are also random variable. Right? So senior statistic are random variable. It has a probability distribution. This is called a sampling distribution. Sorry. Right? Right. So sampling distribution of a mean. If we can take repeated, for example, if we can take repeated random sample from one population and calculate each sample mean, we'll find that the sample mean would vary randomly from one to another. Logically lah kan, it won't have the same mean value. So the sample mean would vary randomly from one to another. Okay, suppose we can simulate an experiment. Let the population, let's say n equal to 100, be the age of individual. Assume that we know the population mean, which is mu equal to 29.5 years old, and the population standard deviation sigma is 13.6. We take 97 random sample of size and equal to 10, compute, and plot the distribution of the sample mean as shown in the following figures. Okay, now we can see the dot there shows that how the sample mean randomly, right? And also the population mean is equal to 29.5. So we know that there is a distribution, sample mean value, some higher and some lower than the true population mean. Okay. However, we know that by calculating the average of the sample mean equals to mu, the mean of SDM or sampling distribution of mean is mu. So therefore, sample mean is unbiased estimator of the mean, right? So how does sampling distribution compare to a distribution of a single observation? Suppose we take in 100, n is equal to n 100 of individual observation and plot the distribution as shown in the figure, right? So we know that this distribution is also centered on the mean. Okay, see that all the dots here focusing on the mean, which is 39.5. Okay, but it is more spread out lah than the SDM, because it's a true sample, not the mean. Okay, but however, if we plot, the sampling distribution, will normally distribute near to the mean, near to the mean of population. Okay, so central limit theorem states that as the sample size increase, regardless of the underlying probability distribution, the sampling distribution of the mean become increasingly normal. So you can see, if n equal to 1, how the value spread out in the graph, and then we increase the value n equal to 10, so it become focusing in the center, and then we increase the value to n equal to 30, now it become more close to the center, right? So it will normally, the mean of population will closely near to the population mean, right? So what is the central limit theorem? This is central limit theorem, right? So it's very fundamental and a key concept in probability theory. It says that the statistical and probabilistic methods that work for normal distribution can also be applied to many other problems which deal with different type of distribution. Alright? So here is another example of central limit theorem. Yeah. So given a data set with unknown distribution, for example, yeah, in the diagram, the first one is uh, let's say a uniform, a binomial, or completely random diagram, or completely random data set. Yeah. For a large sample size, the sampling distribution of means will approximate to normal distribution, even though the population distribution is not normal, even though it's random, even though it's binomial, right? So if we have a population with mean and standard deviation and take large random sample, let's say n equal to or greater than 30, from the population with replacement, then the distribution of sample mean will be approximately normally distributed, right? So why is that the n normally we set at equal or greater than 30 sample? Because yeah, a sample size of 30 is considered large enough to see the effect of power of CLT, central limit theorem. So it's considered sufficient, right? If we set the sample to 30, right? So the closer the population distribution to normal distribution, fewer sample needed to demonstrate the central limit theorem. If the distribution of the population is highly skewed, then we need a large number of samples to demonstrate and understand the central limit theorem. Okay? So what are the assumptions behind the central limit theorem? What are the assumptions that we okay? Before we dive into the implementation of the central limit theorem, it is important to understand the assumption behind this. Okay, the first one, the data must follow the randomization function. It must be sampled randomly. Okay? The second assumption, samples should be independent of each other. One sample should not influence the other sample. It should be independent. The third assumption is that sample size should be not more than 10% of the population when sampling is done without replacement. The fourth assumption, the sample size should be sufficiently large. Right now, how we will figure out how large this size should be, how large the sample size should be. Okay? Well, it depends on the population. When the population is skewed or asymmetric, the sample size should be large. If the population is symmetric, then we can draw a small sample as well. Okay? The first thing is we need to plot the data to see what is the shape of the data set. Whether it's skewed or asymmetric. Right? Right? So this is how we demonstrate the central limit theorem, right? With the n equal to 5 and also 10. Okay, we take the first example. Okay, if the population distribution, the first one, okay, is symmetry. Okay, so the sampling distribution of n equal to 5 will be shaped like that, and also the shape of the sample distribution of mean with n equal to 30 for every population distribution is the same compared to the n equal to 5, right? Why is that this is very important? Why is that it's very important? Right. So the field of statistics, yeah, is based on fact that it is highly impossible to collect the data of the entire population. Instead of doing that, we can gather a subset, only a subset of data from a population and use the statistic of that sample to draw a conclusion about the population. Okay? So in practice, yeah, the unexpected appearance of normal distribution from a population distribution is skewed. Even having a skew, many practices in statistics such as hypothesis testing make this assumption that the population on which they work is normally distributed. Okay? So this assumption basically simplifies matters and we overcome the problem of the data belonging to the population which is not normal. Okay? Thus, even we don't know the shape of our distribution where our data comes from, but according to CLT, we can treat sampling distribution of any population as normal. Okay, of course, yeah, for the conclusion of the CLT to hold, we need sample size to be large enough, right? Okay, so the CLT, central limit theorem, is not limited to making inference from a sample about a population. There are four kinds. We can also do an inference by using the CLT. So there are four kinds of inference we can make based on the CLT. Okay, first one, when we have the information of a valid sample, we can make accurate assumption about its population. Right? Second one, we have the information of the population. We can make accurate assumption about a valid sample from that population. The third one, the third inference, we have the information of population and a valid sample. We can accurately infer if the sample was drawn from that population. Okay. The third inference is that the fourth inference is that we have the information about two different valid samples. We can accurately infer if the two samples were drawn from the same population. Right? So for our first further reading of the application of central limiter, we may refer to this application, right? Okay. Now we go to the second estimation, which is the interval estimate. Okay. Before this, we were discussing on the point estimator, right? So although the point estimator, such as the sample mean, can be used to estimate population parameters, we know that this point estimate is unlikely to be true mean of the population. The mean, the true mean of the whole population. So reporting results statistical test as a single number is unappalling because there is nothing inherent in that provides any clue about how close it is to the true mean, which is mean. So the point estimate could be very close or very far off, right? So one way to avoid this is to report a range of plausible values called a confidence interval, right? Okay, so the confidence interval is used to express the precision and uncertainty associated with a particular sampling method. Right? Confidence interval consists of confidence level that describe the uncertainty involved and also statistic and also a margin of error. Both these and statistic estimate the precision of the method. So we can give this conclusion is that confidence interval is equal to sample statistic plus minus the margin of error. An example of the confidence interval, suppose that we compute the mean height of the man for a sample, which a point estimate for the population of all men in the campus, in one campus. Suppose that we set our confidence level for the sample mean is 95% and the margin of error is plus minus y centimeter. Okay? So therefore, it can be concluded that if the same sample method was used to take different samples and compute different interval estimate, the population parameter mu would be fall within plus minus y cm 95% of the time. Right? So how are we going to interpret the confidence level? Okay? So confidence level describes the likelihood probability that a particular sampling method will produce a confidence interval that includes the true population parameter. Collect sample from population, compute the confidence interval for each sample. Right? Some confidence interval would contain the true population parameter, but some wouldn't. 95% confidence level means that 95% probability that the sample would contain population parameter. 90% means 90% probability that the sample would be contained population. If 99% means that 99% probability the sample would contain population parameter. So, right? So what is the trade-off, between the confidence interval? So confidence level is usually chosen by the experimenter before the confidence interval is computed. Okay, so I have one question. What is the value? What is the confidence value level that we should set? Either it's 95%, 90%, or 99.9%. But it depends on the researcher itself, yeah. If you are confident, yeah, with your sample, right? So normally if the researcher is very confident with sample, it will set at the 99.9%. However, if you're less confident with that sample quality, then it will set at the 90%. Okay, right? So, but in a common practice, we normally set at the 95% confident interval. Right? Thank you and see you in the next lecture. Bye bye.